So this is known as applied optimization when we actually do a word problem for like a relevant real life application of extrema here. So let's say we have a rectangular box and it's resting on the XY plane with one vertex at the origin. I'll draw a picture in a moment. The opposite vertex lies in the plane 6x plus 4y plus 3z equals 24. We want to find the dimensions of the box that will maximize the volume, and then we'll actually find that max volume. Fine. So if I draw a picture of what's going on here, we've got a rectangular box that's lying flat on the XY plane, and one of the vertices is in the plane 6x plus 4y plus 3z equals 24. And you guys should know how to sketch planes in space because, you know, we went over that, right? So if I find the x-intercept, I set y and z equal to 0. So I'm going to get 4 here on the x-axis is the x-intercept. If I set x and z equal to 0, 2, 3, 4, 5, 6, I'll have 6 be the y-intercept. And if I set x and y equal to 0, I'll have 8 up here on the z-axis be the z-intercept. And so the traces of the plane are these straight lines. And this is the portion of the plane there in the first octant. But the box that we want, I didn't draw the box yet. I'm going to in a minute. The box is behind this plane I just drew. So it's lying flat here with this one vertex here in the plane. This vertex right here is in the plane, the red plane there. So can we maximize the volume of that box? And so what I'm going to do is I'm going to call one of the dimensions x along the x-axis. That could be like a width. And then along the y-axis, we'll do a length, say y, and then a height z. So the volume is x, y, z. And this is what we want to maximize. This is the quantity to be maximized. A big mistake that students make, especially with word problems, is they start just reading and then they don't want to really understand or comprehend what the heck. And they just start writing stuff down and then doing math willy-nilly without thinking. So the plane equation they gave you there, the 6x plus 4y plus 3z equals 24, you're not to maximize that equation. Like you don't want to do any calculus on that. Okay, that's just the what we call the secondary equation, also known as a constraint, because it's constraining our box, aka the constraint equation. It's not the quantity that you're trying to maximize or minimize. You're trying to maximize, in this case, your volume. Now, the problem with the volume formula right now is this volume formula shows us that the volume is really a function of 3 variables. But what we've learned in this last week is we've learned how to find extrema for functions of 2 variables only. So we're kind of screwed right now. It's like, I can't find extrema for a function of 3 variables. What the heck? So the trick is to use our secondary equation and use it to help reduce our primary equation, the equation to be maximized here. I'll call this the primary equation. So what we're going to do here is I'm going to solve the plane equation for z, and then I'll substitute that z into my volume function and thereby reduce it to a function of 2 variables instead of 3. That's the plan. So when I solve the plane equation for z, I'm going to get 1/3 times the quantity 24 minus 6x minus 4y. I did that pretty quick, so hopefully you can follow how I did that. I just subtracted the 6x and 4y from both sides and multiplied both sides by 1/3. So what you're going to do now is you're going to substitute this into the volume function. And so your volume will now be a function of 2 variables only, which is good. It's going to be x times y times this 1/3 24 minus 6x minus 4y. Okay? And now we're going to do calculus on this. So what do I mean? Well, we're going to get Vx and Vy, the first partials, simultaneously set them equal to 0. And we'll get, in this case, a nonlinear system of equations. Solve the nonlinear system in order to get a critical point or critical points, and then do the d-test to see if it really is a max. So there you go. That's the process. Now, before I go ahead and do the partials here, I'm going to distribute the xy over this difference. I'm not going to distribute the 1/3. You can if you want. I'm just going to leave it as a multiple, just because I don't like to deal with fractions. But after distributing the xy, let's see here. I have 24xy minus 6x squared y minus 4xy squared. Yay. Now what? Get the partials. So partials. And we're going to get 2 Vx and Vy like that. Okay, and the 1/3 is part of the answer. I just have it as a multiple. Okay, so 1/3 times whatever the partial is with respect to x of this big old expression inside the parentheses. Let's see, the derivative of 24xy with respect to x, I believe, is 24y. Minus the second term, I think it's going to give us 12xy, and then the last term, partial derivative with respect to x, is the minus 4y squared. Okay, and we'll set this mess equal to 0, and then get the other partial. So we'll still have the multiple of 1/3. Partial with respect to y now, 24x minus 6x squared minus, oh boy, what do we got here? 8xy. Equals 0. Okay. Everybody okay so far? We got a nonlinear system, man. This is a hot mess. Now, of course, you can kill off the 1/3. Multiply both sides of these equations by 3, and the 1/3 is gone. Okay. But you're still left with these two equations, and it's pretty gross. So what I'm going to do is I'm going to use the ZPP. You know, zero product property is going to be your savior here. So for Vx, when I rewrite Vx by factoring, I could factor out a 4y, but I'm just going to factor out, so I'll just say here, I'll multiply both sides of both equations by 3 to get rid of the 1/3. So people don't ask me, what happened to the 1/3? I killed them off. So get rid of it. Okay, now what? So if I factor out a y as a common factor for the partial with respect to x, Vx, that is, I'll get the other factor is 24 minus 12x minus 4y. You'll see in a moment why I'm doing this. And then from the other partial, I'm going to factor out a common factor of x. Still set that equal to 0. Okay. Now, when you, in your head, imagine, you know, you're using the zero product principle. Something times something equals 0, then you can easily set both of those factors equal to 0. So one of the things that comes out of this one is y equals 0, or of course, the 24 minus 12x minus 4y equals 0. Sure. And then when I do the applying the ZPP to the other partial, I got, okay, x equals 0. Or the 24 minus 6x minus 8y equals 0, or they both do, fine. I hope you can see that right off the bat, if we let x and y both be 0, the point 0, 0 is indeed a critical point. Like it'll make the system satisfied. It's a solution. It's a critical point. Now let's think a little bit though. I don't even want to bother with this critical point for this real life problem. If this were just a regular problem, you know, very theoretical and conceptual, 0, 0 would be a very legitimate critical point, and I would do the d-test on it, and I'd do the whole 9 yards on it. But I'm not for this problem. Why not? Why am I going to ignore it for this real life situation? What do the x and y represent in this real life situation?
Length.
Yeah. I mean, do I want a box that has a 0 width and a 0 length? Because that's what the x and y down here are representing for my box. It doesn't really seem like I'd be maximizing my volume, does it? I'd probably be minimizing it. But I don't want to minimize it. I wanted to maximize it. So bummer, you know. Now, if they asked me to give both the max and min for this problem, I would keep it in and I'd go ahead and deal with it and perform the d-test on it. But it's kind of like, oh man, I don't want a zero or a flattened out point for a box or something. So I'm going to ignore it. Okay, fine. Now what? Well, how do I get there's got to be other critical point or points. And so yes. And so the other factors, when we set them equal to 0, that's a system of equations. Let me rewrite them because I like it where it's written where the variables are on one side and the constant on the other. And so if I do that, this is an easy peasy linear system that you probably saw in a beginning algebra class. And easy to solve. Okay, so let's go ahead and solve this linear system of equations. And you can use either the substitution method or the elimination method. I'm okay with either, but just show your work. Okay. So let's see here. If I wanted to evaluate one of these variables here, how about if I multiply both sides of the second equation by -2? Okay. So then what? Well, the first equation I'm not touching. I'll just copy it down. And then after distributing the -2, and I'm doing this because I'm using the elimination method here, I'm going to add these two equations together. You've seen this in algebra. And I'll eliminate the x variable. So because 12x plus -12x is 0. But then I'll have 4y minus 16y. That's 12y. And then when I add the constant terms together, see 24 minus 48, I get -24. Oh, cool beans. Now I can solve for y. And so the y coordinate is a 2. Wonderful. Now what? I need to get the corresponding x coordinate. Well, how do I do that? You can just substitute this y equals 2 back into either of the two original equations. It's up to you. How about I'll substitute it into the second equation, the 6x plus 8y, but I'll substitute y equals 2 in there. So I'll 6x plus 16 equals 24. And then if I subtract 16 from both sides, I get 6x equals 8. And then divide both sides by 6, reduce to lowest terms, and I get x equals 4/3. So what I'm saying here is the point 4/3 2 is a critical point. Now, is it going to maximize my volume? Like, don't guess. Like, I don't know, probably. It looks good to me. On your exams and quizzes, I will ask that if you're being asked to optimize something, unless we're using Lagrange. Lagrange, you don't have to do the d-test. You'll see. Here, you got to use the d-test, like prove it. So prove it's a max by doing the d-test. You know. Prove it to me. Don't just say it. Saying it doesn't prove anything to me. I'm like, yeah, I'm not impressed. Okay, so what are we going to do? So we're going to get, let's go ahead and get these second partials, vxx, vyy, and vxy, then we'll put it all together. So vxx is the derivative of vx. Now remember, our vx was way up here. And if I take the second partial of that with respect to x, I'll still have the 1/3. And then it looks like I'm just going to have -12y. So I'll have the 1/3 times -12y, but that looks like it'll give me -4y. If I find vyy, so that means I need to take the partial of vy right up here, but with respect to y, and the 1/3 still there, and it looks like I'll get 1/3 times -8x. Yeah. So that's going to give me -8/3 x for vyy. For vxy, which you know is going to be the same as vyx, so whichever one you want to get, I'll get vxy. So I'm looking at vx. I'm going to take the derivative of vx with respect to y. So I'll still have the 1/3, and then I'm going to have 24 minus 12x minus 8y. Okay, so it's going to look like this. 1/3 times the quantity 24 minus 12x minus 8y. So when you put this all together, because d is going to be vxx times vyy minus the second partial the mixed partial vxy getting squared. If you just for kicks and giggles, if you did evaluate this at 0, 0, what would happen? And I claim you would get, well, this would be 0, this would be 0, and then this one would be, I think it would be 8. So you'd get a negative number. And so what does that mean? You actually don't have a minimum at 0, 0. What do you have? Not a min. What happens when D is negative?
Saddle point.
Saddle point, yeah. But remember, we kind of don't care about the 0, 0 because it's not very interesting to have a box with 0 dimensions. So, but I did want to just show you what would happen if you evaluated at 0, 0. So let's do the more interesting one. What happens when you evaluate D at 4/3 2? So you're going to get, you know, negative 4y, so that's negative 4 times 2 for the vxx, and then the vyy, negative 8/3 times x, but that's 4/3, and then minus your, ooh, this is going to be terrible, your vxy 1/3, and you're going to plug in your 4/3 2 in here. Ugh. Yeah, I know, it's tedious. Okay. So then it's going to end up, after you punch this all up in a good old calculator, because who wants to do this arithmetic? Not me. I get like negative 8 for the vxx, negative 32/9 for vyy, minus, I think I get 64/9 here. This is going to end up being 64/3. Oof, okay. And I don't even really care about the number. I really just care about the sign. So that's a positive. So then what? Well, good news, that means we have either a max or a min on our hands. So to figure out the rest, you have to evaluate the vxx at the critical point, and that will help determine if you have a max or a min. And so I claim you will get, so when you do your vxx, you get negative 4 times 2, but that's negative 8. That's a negative. And so when vxx is negative, but your D is positive, you do indeed have a relative max. Yay. But we're not done with this problem for the following reason. They wanted us to give all of the dimensions for the box. So we got the X and the Y, but we don't have the Z. And we also need to give the actual max volume. So I claim once I get the Z, I'll be able to quickly get the max volume. So how do I get Z? Well, remember, Z has to satisfy the constraint of that plane equation. So when you evaluate Z at the point when X is 4/3 and Y is 2, I claim you will get, what do you get? I didn't write it down. Oh yeah, I did. You'll get 8/3. So Z is 8/3. Now they didn't give us any units for this problem. They didn't tell us if it was in meters or feet. So this will be a unitless box. But the volume is basically going to be given the dimensions 4/3 by 2 by 8/3. So there's all my dimensions. And this max volume is going to be 64/9. Units cubed, whatever the units are. Don't know what they are. They didn't tell me. Okay, and we're finally done with this problem. Oops, did I write 60? That's a 64. 64/9 units cubed. Okay, and we're done with this word problem. Okay, there you go. It's optimization. We're going to do this problem all over again. Probably not today, but Friday, in a much easier way. Okay. Questions? Is anybody there?
Yeah, we're here.
Yes.
You're still alive? You're hanging in there?
How did you get Z again?
How did I get Z? Good question. Remember Z, remember we solved for Z with the plane equation way back here?
Yeah.
Z had to fulfill the fact that Z is equal to 1/3 24 minus 6x minus 4y.
Yes.
And we evaluated that Z when, because we already found the X and the Y, thankfully. Plugging in our X and Ys, we get 8/3.
Oh.
Yeah, I did it kind of quick, sorry.
Okay, I got it. Thank you.
Yeah. So any other questions on this one? Okay.
Solve for
Well,
Z.
go ahead.
When did we solve for Z?
We solved for Z way back here, Nathaniel.
Oh,
Can
I see.
you see my screen? Okay.
Yeah.
Okay. So normally I skip the rest of the word problems, but because word problems are kind of tricky, I think what I'll do for you is I'll do one of these other word problems I have on here because students get a little scared with these kinds of situations. So let's take a look.
Definitely not the worst thing.
Let's see if I have it. I'm going to skip 12 because that's easy. Good luck. And you're welcome to come to my office time if you want me to do it. I'll do it for you there. But let's do example 13 because it's kind of tricky. And you should know how to do this, though. And yeah, I'm going to give you a similar quiz problem. So you better know how to do it. Like, pay attention. Okay, it sounds kind of hard, though. I'll read it to you. Oh, my God. Now, they gave us the answer right there. But, you know, how? So a home improvement contractor is painting the walls and the ceiling of a rectangular room. Now, remember, they're not going to paint the floor. Okay, so we're going to disregard the floor. Well, we're going to put carpeting on the floor. Okay, fine. The volume of the room is 668.25 cubic feet. Ooh, that's weird. The cost of the wall paint is 6 cents per square foot. And the cost of the ceiling paint, I guess that's more expensive, 11 cents per square foot. Fine. Find the room dimensions that would result in a minimum cost of paint. Now, this is sort of a reverse problem because usually you want to figure out what's the cheapest paint to minimize your paint costs, not, well, I guess I'm going to have to shrink the room, Martha, in order to minimize my paint costs, you know. Like you get to pick the dimensions of your room that would minimize the paint. But if you could, what kind of room dimensions would you pick in order to result in a minimum cost of paint? Now you are constrained because they told you the volume of your room. You can't just say, oh, I want like one of those. Have you seen those reality TV shows where they have those little miniature houses and people actually live in these little tiny houses? Anybody?
Yeah.
Yeah.
You can go,
Yeah.
yeah, I'm going to minimize my paint costs. I'm just going to get me one of those little tiny houses and then I'm set. Not much money to paint those, but let's say you don't have that option because they're telling you that the volume must adhere to this 668.25 cubic feet. Fine. So that, folks, is your constraint. Your constraint is that volume is going to be length times width times height of your room, and it is 668.25 feet cubed. You don't have a choice. You have to have it, which is a pretty nice, big, large living room. Okay, fine. You don't do calculus on this. This is what we call your secondary equation. It's your constraint. So please don't try to do, you know, oh, let's go find the first partials of this formula. No, 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 no. You don't do that with the secondary equation. Now, the cost, which we'll call big C, is going to be, now you got to think about this. Let me draw a picture here of a room. Here's length, width, height. Okay, so the walls, and there's 4 walls here, you know, are going to cost us 6 cents per square foot. So we're going to do it by area. So let's first do the wall, this wall right here, which has area WH. And keep in mind, there's 2 of those because you got the back sides. You got 2 WH, those areas, but you're going to multiply that by 0.06 because that area there, the front and the back here that I've shaded in pink, that area, whatever square foot it is total, is costing us 6 cents per square foot to paint. Okay, so so then what? So this is our cost function here. Plus, now we're going to paint this side wall right here, but that looks like it's got area length times height, but there's 2 of them because you got that back side over there. So 2 LH of those guys still costs 6 cents per square foot to paint because it's the walls. Now let's talk about the ceiling. Oh my God. So the ceiling here looks like the area of it is WL. There's only one of those, not two, one ceiling. You're not going to paint the floor. But the ceiling square footage costs us 11 cents per square foot. So folks, this is the cost function right here. We're calling it C. But the problem we have right now is C is a function of three variables, W, H, and L, all at the same time. It's like, uh-oh. And we only know how to optimize. In this case, we're going to minimize because we want to minimize the cost. We have to optimize functions of two variables only. So we're like, uh-oh, we need to get rid of one of these variables. Does it matter which one? No, it does not. Just kill off one of them. Well, how do we do that? Do we just erase them? No, you don't erase them, for goodness sakes. What do? You use the secondary equation, which is, and I'll use this right here, and solve it for your favorite variable, whichever one that you would like to kill off. And it's up to you. You're the boss. You figure it out. It's all going to come out to the same answer most of the time. I will say, I'll mention something later about how if you pick the wrong variable to kill off, you could get different answers. It's not perfect. That's why Lagrange is a better method, but we'll learn that soon. I'm going to kill off the variable H. So I'm going to solve for H using our volume constraint equation. And when I do that, I get H is equal to 668.25 divided by LW. And what am I going to do? I'm going to substitute this into my cost function everywhere I see the letter H. And there's two spots. So this cost function is going to get kind of messy. But at least I'll only have a function of two variables, W and L, okay? So if you don't mind, this first term, since it doesn't have any H's in it, I'm going to list that guy first, and I'll rewrite it with the coefficient in front, 0.11 LW, plus, and then these two terms in the front here, I'm going to factor out a 2 and a 0.06, since that's their common factors. And then what? Well, I'm going to have, for the first guy, I don't want Adobe. What am I doing here? W times the H. And so the H is 668.25 divided by LW. Plus, and so I'm going to factor this out. So I'm going to pull this out. Plus the other term, which we also factored out, the 2 and the 0.06. Okay. And what does he have? He has L times the H, which is 668.25 divided by LW. Okay, boy, this is a hot mess. And these problems are very typically like this, so like, don't get alarmed, all right? Now, what am I going to do? Well, I'm going to do a little reducing and cleaning up, not much, but, you know, some. So notice that the W's are canceling right here, like that. And the L's are canceling like that. Okay, fine. Then what? Well, you know, it's still kind of a hot mess. So if I clean up my cost function a little bit, although it's still kind of messy, because I now have fractions in there, which is kind of a bummer, but whatever. 0.11 LW plus, and this is the same as 0.12 times 668.25 divided by L plus 668.25 divided by W. Okay, that's pretty gross. Now what? Go get the partials, set them equal to 0, find the critical point or points, and perform the d-test. And hopefully you can minimize your cost. Oh man, are you kidding? No, I'm not. So what's next? We'll go get the partials. Now the partials are going to be a little bit yucky because these two terms here, when you get the partials, you're going to kind of run into a mess. So just to remind you that it might be good for you to rewrite these so that when you have to take the derivative, you will use the power rule from Calculus 1. So let's get CW, so the partial of cost with respect to W. So that looks like it's going to be 0.11L plus 0.12, the first term doesn't have any W's in it. So that first term's this guy right here, with respect to W, that partial goes to 0. And then the other term isn't going to go away. So you'll have the multiple 668.25 and then -1 times W to the -2. I know, pretty gross. So this is looking like 0.11L minus 0.12 times the 668.25 divided by W squared. Oh boy. Yeah. And you're going to do a similar thing to get the other partial. So I get 0.11 W now, plus, and then doing the similar thing to that first term, I'll end up with a minus. Let me put a minus right now, 668.25 all over L squared. And the other term goes to 0 when you take the partial with respect to L. Fine. Okay, so now what? So you're going to solve simultaneously. You're going to go, okay, I just set both of these to 0. Oh, God, are you kidding me? No. No. Well, what do we do now? I'm stuck. You know, I get students, they get this far and they're like, I don't get it. And it's like, yeah, you do. It's algebra. You know. No, I don't. I'm stuck. Cracks me up. Well, you're going to use the substitution method, you know. Pick one of these partials that you'll solve for, you know, your favorite variable. It doesn't matter which one. How about this guy, this first guy, if we solve it for L, let's say, fine. So then what? Well, you add the 0.12 times, I'm not even going to bother multiplying these out, to both sides. And then you divide both sides by 0.11. So you get this yucky quantity is your L. Yuck. Then what? Well, then you substitute this into the other partial in place of the L. Oh man, are you kidding? No. It's gross. So if I do that, let me stick to 0 for a second. So I'm going to have 0. So when I substitute that big old quotient in place of the L, and then I'm going to have to square it, which is really, I know. Like that, you're like, oh man, that's just, ugh. Yeah. But the good news is this all does come out in the wash. You know, it's like, oh, really? Yeah, well, if you do rewrite this thing, so I'm going to turn this into a multiply problem by multiplying by the reciprocal. So you're going to have W squared here, and then you'll have 0.11 squared, and then divide by 0.12 squared, and then you'll have your 668.25 squared equals 0. So I hope you can see you can do a little bit of reducing here. Oh my goodness. Really? Yeah. Well, one factor of 0.12 goes away. That's nice. One factor of that 668.25 goes away. And that looks like that's it. So then what? Can you say the ZPP? I know you could. So if I factor out a common factor from this equation, I'll get, 1 minus, I factored out a 0.11 W, so I got to remember that. Like that. And then you know, if something times something equals 0, well, then you set each of these factors equal to 0. So 0.11 equals 0 means the width is 0. But again, as before, we're trying to have the W be a width of a room. It's not very interesting when your width is 0, but it would lead to some critical point. And then this other factor, which is like, oh, wow, you're kidding me. No, I'm not. So this has to equal 0. So that's how you figure out, well, okay, now at least we can get W. So once you move this term to the other side, and then what? Well, and then you'll multiply both sides by 0.12, 668.25, and then divide both sides by 0.11. You'll get some horrible number. And it turns out this number, and you can check me on this if I did this all correct, it should be a 9. Really? Yeah. And since this is a problem with units, 9 what? What's the units?
Feet.
Feet, yeah. So it'll turn out where your W is 9 feet. Then, well, how do you get your length? Oh, well, remember we solved for length up here. And so if you substitute W equals 9 in this L formula here, believe it or not, you'll get L also equal to 9. Can that happen? Sure. But then the H will be different. Well, then how do you get your H? Well, recall that LWH was supposed to equal 668.25. And if you've got 9s for both your length and your width, then you can substitute that into the volume formula and you'll get that the H, the height of your room, not a bad height for a room, is 8.25 feet. Now, what is the actual minimum cost? Because we did find the dimensions of our room. So our dimensions of our room are 9 feet by 9 feet by 8.25 feet. So here's our dimensions. And that was one of the questions they asked. Remember always to answer all the questions they ask you in a word problem. Don't leave parts of it blank. What about the minimum cost? Well, remember that we did get cost in terms of all three variables. You could either plug it back into this original cost function, or if you prefer the one where we reduced it to two variables. Either way, this point is a critical point. Okay, so the cost ends up being $26.73, which is pretty cheap for paint. That's hard to believe. The paint could be that cheap. I don't know. I've painted parts of my house and it's never that good. Maybe it's just cheap paint. Okay, so I'm done with that problem. I just wanted to point out that sometimes when you're solving some of these nonlinear systems, it does get a bit messy. Okay, and that's the point. I'm going to skip absolute extrema because I don't have time. But you did discuss absolute extrema when you took Calc 1. So don't worry, I won't put it on any test or quiz. Okay, so that's the good news. No absolute extrema. We're going to move right on into Lagrange multiplier method. Yay. Good stuff. So I hope that you're getting that this relative extrema stuff is not too bad. I mean, you do have to know some algebra, and that's maybe the part that makes it a little tedious, but I think it's kind of fun personally, but maybe that's just me. Okay, so now we're going to do the last part of chapter 15. Congratulations for making it this far. Section 15.8, the method of Lagrange multipliers. So what about it? It's another way to find extrema, but it is restricted. No pun intended. What do I mean? Well, it turns out that in order for you to use the method of Lagrange multipliers, you can't just use it whenever you feel like it. It has to be the kind of problem where you're trying to optimize with a constraint or more than one constraint, one or more constraints. Otherwise, you're not allowed to use it. So, okay. So how does that work? Well, we're gonna look at a problem right now with a constraint, and we've already done some constraint problems. Oop, there we go. So before we start here, let me just point out that the last two word problems I did involved a constraint. So when we did the volume of the box that was resting on the XY plane, there was a constraint. The other vertex was constrained by that plane. We could have done that whole problem using the Lagrange method. It would have been a perfect candidate. In fact, that particular problem I'm going to do over again, and not right now, but I will using Lagrange. And I think it's easier and cleaner when you do Lagrange. Okay. The problem I just did with the paint, that's a constraint because the volume of the room was constrained. It was given to you. That's considered a constraint. So that would have been an excellent candidate for Lagrange. Well, it sounds like everything is an excellent candidate. No, it isn't. Last lecture, when I did the word problem involving profit, and we did maximizing the profit for that word problem, where there were two products, a certain number of units for product A, certain number of units for product B, that problem cannot be done using Lagrange. Forget it. Don't even think about it. Well, why not? There's no constraint. They just said, go find the profit. They didn't give you any other information that was constraining that profit. So that problem, you had to do it the way we did it, which is basically get the partials, get the critical point, and perform the d-test. There's no other method for that kind of problem, okay? I remember I used to, this is many years ago, I had a student in my calculus class, and they ended up wanting to be a business major, or maybe they had been a business major, and so they told me that their business an economics professor, because I guess they had come from a 4-year, was really adamant about students knowing the difference between when can you use Lagrange and when can you not. And I guess this professor was really hot on the trail for making sure that students knew the difference and would, give them both kinds of problems on an exam in order to see, or trick the students into, see if they really knew what they were doing. And I just thought that was interesting, especially with a business prof doing that. So I'll just pass that on to you. Know the difference. Because if a business major can know the difference, certainly you can. It's not that hard. Okay. So what of the Lagrange multiplier method? So this lecture that I'm going to give to you is mostly prepared and stolen from, with all acknowledgement to Dr. Arnie Vallone of blessed memory. He passed away 8 years ago, but he was my mentor, and I'm still in touch with his wife, and good people. So he did this lecture basically 10 years ago, and I co-opted it basically for my personal use because I just thought it was really nice the way he presented the material. It is very different from the way your book presents it, okay? And I'll point out the differences, and I will also say that I prefer that you do my method when you do quizzes and exams, okay? Here we go. We'll start off by what you know, and then we'll go to what you don't know. So what do you know so far? You know that finding relative extrema for a function of two variables, you got to get your first partial with respect to x, set it equal to 0. And then you get your first partial with respect to y, set it equal to 0. Fine. And then you, after you've solved that system, go do the d-test and figure out what kind of extrema you've got. Fine. With Lagrange multipliers, it's a totally different approach. Okay. You already know there's going to be a max and a min, possibly. You might even be asked for both. So you don't ever use the d-test at all. Really? Yeah. In fact, you'll never have to bother getting second partials with the method of Lagrange, which is kind of cool. The first partials, yes. Second partials, no. So the other cool thing about Lagrange that I must tell you right now, because it's exciting, is that if you're given a function of 2 or 3 variables, or even more than 3, as long as there's a constraint, you can go get the extrema. So, well, who cares about that? Well, you care, because in the last 2 problems that I just did for you, those last 2 word problems, remember, initially the quantity to be optimized was a function of 3 variables. Like the volume one, we had to go reduce it to a function of 2 variables before we could do the calculus on it. With the paint problem, initially our cost function was a function of 3 variables, and we had to go in there and reduce it to a function of 2 variables. Lagrange, you never have to do that. You never have to do that. You can actually find extrema for functions of 3 variables or more without having to reduce them back to a function of 2 variables. And this is what makes Lagrange so awesome. Okay. So let's start with an easier, and somewhat easy problem, and then we're going to stop doing the problem and note that it's going to be a pain in the rear end. Okay, so what do you mean? So let's say you're given 1,000 square feet of material. That's going to be a constraint, people. There's your constraint. And you want to make a rectangular box. Okay, so you've got your rectangular box here. Okay, fine. What are the dimensions of the box that will maximize your volume? Okay, so your volume will be, let's do the X, Y, Z for our width, length, and height. You can pick LW and H if you prefer, as long as you have 3 variables. Now, again, we want to have a box that isn't, boring, you know, with 0 as a dimension. So we want x, y, and z to be positive. Fine. So you only have 1,000 square feet of material. So you have to figure out a way to construct this rectangular box. You know, do you want to make the base really large and have the base of the box use up most of the material and then have, you know, real skinny sides? Or do you want to have a small base and make the sides of your box, you know, large? So you got to figure out how you're going to use this, most of this material up. Okay, so what of it? Well, because they gave us a constraint, which happens to be square feet, that means that our constraint is surface area. So what is the surface area of a rectangular box? So if you use the fact that there's basically 2 of everything here, you're going to have 2xy plus 2yz plus 2xz, and that's constrained. That has to be equal to a 1,000. This is the constraint equation. Don't have a choice. Okay, and we want to maximize volume subject to the constraint. Now, if we were doing it the way that we just did the first 2 word problems today, we would have to reduce the volume to a function of 2 variables. So let's just start doing this, and then we're going to stop and go, no, after we look at it. So we're going to reduce V to a function of 2 variables. And it's like, oh man, really? Yeah. How? Well, use your constraint equation and solve it for one of the variables. So here's your constraint. And you can solve it for any of the one variable that you like. Although traditionally, as you've noticed, they usually solve it for z, but that could lead you into problems sometimes. But I'm going to rewrite this equation. I'm going to first reduce it by dividing both sides of the equation by 2. And then I will, let's just solve it for z. What the heck? So you'll notice the 2 terms that have a z will keep on that side of the equation, and we'll subtract xy from both sides of the equation. And then from the 2 terms that are still left on the left-hand side, we'll factor out the z as a common factor. And then finally, we'll divide both sides by y plus x. So here is your z. Now, why is this going to be a big pain? Because now when you substitute this into your volume equation for z, since your volume is xyz, your volume is now reduced to a function of 2 variables. So you could do everything that we've been doing this last week. Go get the partials, set them equal to 0, and then do the d test. But do you see right now that you're going to have to use the quotient rule in order to take the partials here? So Vx and Vy are not going to be very fun to go get. We'll need the quotient rule, and it's just going to be a big hot mess. Okay, and I don't feel like doing the rest of this problem because it's just going to be very messy and very tedious. Okay, so we're going to stop right there. We're not going to finish the problem yet, and we're definitely not going to do it where the volume is reduced to this function of 2 variables here, because it just looks like the partials are going to be a real pain to even go get. Okay, fine. Now, just a little stopping point, because Arnie, Professor Vallone, used to stop and go, hey, how come it's always z variable is the one that gets killed off? That's totally not fair. That's just not right. and in fact, so I'll just put not fair. In fact, sometimes when you solve for this traditional variable, you can actually get the wrong answer. For those of you who want to talk about this, like if you're a math major, you definitely want to know about this, because in this advanced calculus book, which I have in my notes right here, a little copy of the one case where you will get the wrong answer if you do that. It can happen. So that method can be dangerous when you start reducing your function to lower number of variables. Okay. So what does Lagrange do? What about Lagrange? So Lagrange, and he's the guy who discovered this method, he tells us to do something totally different. And it's going to start by when I tell you what's going to happen here with this blank, you're going to go, wow, this sounds like it's making it more complicated. And it kind of does, but it turns out it makes it more streamlined. So he tells you to introduce a new variable into the whole situation. Not to reduce out the z, but introduce a fourth variable. We already got x's, y's, and z's. Okay, we already have 3 variables. Okay, now we're going to introduce a fourth variable. Oh, you're kidding me. No, and it's called lambda, and lambda is a Greek letter for the Greek letter L, named after Lagrange. And please learn how to write a lambda correctly. So when I read your paper, I know what you're doing there. That's a lambda, and that's the Lagrange multiplier. What the heck? We're going to have a fourth variable now? This sounds really complicated. Okay, so the way that Dr. Vallone is going to have us do Lagrange is going to be where we're going to extremize, not a real word, but optimize essentially, a function of x, y, z, and lambda. So 4 variables. Subject to the constraint, and the constraint is typically called G, and usually you want to get it into that general representation of a level surface where everything's on one side and 0 on the other. And so we're going to create this brand new function that's a function of 4 variables here, and we're going to call it the Lagrange function. It's a big mother of a function. Big L, function of 4 variables, and the way you're going to construct them is you're going to take big F, that's the equation to be maximized or minimized, and you're going to subtract this lambda, this brand new variable, lambda, times your g of x, y, z, after you've rewritten the g where everything's on one side and 0 on the other. So you're actually going to do calculus on this big mother of a function, as Arnie used to say. But it's 4 variables. I know. You're going to have to get 4 partials and set them all simultaneously equal to 0. Yeah, it's going to be 4 equations and 4 unknowns. I know. Terrible. Okay. So in this box problem that we were just doing, so just go back there. Who's going to be the big F function for us? So here's the box problem, okay? The big F function, the quantity to be optimized, in this case, maximized, is the volume. So V equals XYZ is going to be the big F for us. And then the constraint, when we rewrite it where we get everything on one side and 0 on the other, and I'm going to use the version where I kind of reduced my constraint by dividing both sides by 2, just because it looks a little prettier. And if I subtract 500 from both sides of that equation, so I can get everything on one side and 0 on the other, my G is going to look like XY plus YZ plus XZ minus 500 equals 0. Whew. Now what? Now, the good news here is we don't have to solve for the Z variable. There's no need. Don't bother. You don't have to. So instead, we're going to find all the partial derivatives of the Lagrange function and set them all equal to 0. Okay. Now, using the generic Lagrange, because I'm not going to do the box problem yet. I put that one on hold. Here is your generic Lagrange. It looks pretty nasty. But if you get all the 4 partials for that, guys, you're going to get LX, LY, LZ, and L lambda. Yep. So what of it? Well, the big F, XYZ, is going to have, it's a function of X's, Y's, and Z's. So you're going to take his partial with respect to X minus, and remember, lambda is a constant multiple. And then you're going to multiply that by the partial of big G with respect to X. And of course, you'll set this equal to 0. And then you're going to do the same for the other partials. The big L, the big mother of a function, Lagrange functions, partial with respect to y, Ly, is Fy, sorry, it's not an equals, whatever that is, minus this Lagrange multiplier lambda times the partial of g with respect to y, set it equal to 0. And then the partial of L with respect to z is the partial of f with respect to z minus lambda times the partial of g with respect to z. Set that equal to 0. And finally, you want to take the partial with respect to lambda. Now, lambda is a variable. Oh, yeah. Well, it's some variable. So if you're going to take the partial of big L with respect to lambda, you're going to hold x's, y's, and z's constant, and you're going to differentiate this with respect to lambda. So the big F, since big F doesn't even have any lambdas in it, his partial with respect to lambda is 0. Minus, then when you take the partial of lambda times big G with respect to lambda, and lambda, remember, is a variable, you'll just get the g, because g looks like some multiple, okay? And you'll set this equal to 0. Now, folks, this equation, when you multiply both sides by -1, what do you end up getting back?
The function of g.
Yeah, you get g, x, y, z equals 0, which is your constraint equation. This is all your original constraint equation, and that'll always happen. Anytime you get that fourth partial of your big L, it will end up being the constraint. But that's part of the situation. That's part of your system of 4 equations and 4 unknowns. Now, for those of you who are like, oh my God, I'm not even that good at solving 2 equations and 2 unknowns. Here's some good news for you. Nobody ever asks you to actually solve for the lambda. Very few people are interested or care what the lambda is. Instead, I want you to think of lambda as being an angel variable who comes down from heaven to help us out. And then when he's done, he goes back to heaven and we're good. Okay, so we rarely have to find out what lambda is. Okay, now that being said, economists and physicists care about the actual value of lambda. Okay, the economists, they use it for their own purposes, and okay. And I'm usually, I never ask you for lambda. There might be 1 or 2 homework problems where they'll ask you to go get it, but usually nobody cares. Okay. Now, we're also going to assume that the problems that we're going to be working on will have functions whose gradients are not equal to the 0 vector, because that is not okay. So the gradient of f, which we also can write del f like this, will not be the 0 vector. And we'll also assume that the gradient of g, which looks like this, is not the 0 vector, because we want to avoid problems. Now, I want you to notice that these first 3 equations, if you rearrange them a little bit, you rewrite them. I'm just going to rewrite the first 3. Watch closely, because this is how your book is going to present it. And I don't want you to think that my lecture is completely different from the book, because it's the same. They're going to meet right here. This is where they meet. I want you to notice this. What are you saying here? You're basically saying that the vector with components fx, fy, fz will be equal to, or the same as, lambda, the Lagrange multiplier, times the vector with big G's partials. And remember, this vector I just wrote on the left is del f. You're saying the gradient of f will be equal to lambda, that Lagrange multiplier, times the gradient of G. And this is basically the theorem that you'll see in your book. And I'll tell you right now, I will not be inclined to give you full credit if you just use the way the book does it. More inclined, I want to see when you do my problems, I want to see your big mother of a function, big L, the Lagrange function. The book doesn't do it like this. They immediately have you do this, which is the same as this. Okay. Now, the way I'm teaching you, by the way, is not like, oh, this is like a niche market. Nobody else teaches it like this. Actually, they do. I think there's an author I I met her, Lial, good mathematics textbook author. I met her at a convention, and yeah, her book does this. Okay. So I just want you to know that your text presents it like this. They tell you to take del F and set it equal to lambda del G. Okay, I'm ready to finish the box problem. And then after I finish my box problem, we'll be done for the day. And then I'll do much harder problems on Friday. Now, I know a lot of you are eager to start spring break, as am I. But please don't miss Friday. Okay?
Professor?
Yeah.
Sorry, I don't mean to interrupt, but your camera moved, so we can only see the side of your room.
Yeah, so what?
Oh, I just didn't know if you were talking, like, it's so weird when you're talking to us.
And you get to see my room over here, which is a hot mess.
Yeah,
I know,
sorry.
right? I'm having a lot of problems with my camera right now for some reason, and I apologize for that. I just need to get it together here. I'll try one more time.
I'm sorry, it's just that I see you moving, and I know you're, like, looking directly at the camera, so it's just weird just seeing the side of your house.
Yeah, I know. Well, this isn't the side of my house. This is the side of my ugly office in here. I apologize for that. So let's see if I can't get my camera together. Is that better?
Yeah, sorry.
Much better.
Yeah, this office of mine, I've got, this is like, this room is only like 12 feet by 12 feet. It's supposed to be a baby room. It's a baby's room off of the master. And so I turned it into my office, and I've got like, it's nuts. I got like 4 bookcases all over the place. See that? And I've got like 4 Pendaflex file folders with every single exam I've ever created in my 25 years of being a math professor. It's just it's a nightmare. And my camera is a hot mess. Okay, so is that better?
Yes.
Thank you.
You don't like looking over here in the corner where my trash can is? Okay. So any questions so far of what I'm doing here? You guys kind of get the structure of the Lagrange method? Because we're going to do it right now for reals. Like, let's go for it. So back to the box problem. And as Dr. Vallone would say, time for hand-to-hand combat. Okay, so we're going to maximize our big F, which is volume. Subject to the constraint of, here we go again. It's back. It's not good. Problems now. Come on, please stay. Please, God. Please, God, stay. So the constraint, which we call big G, X, Y, Z, this is the surface area. They gave us a certain amount of material. We're constrained by that. Fine. So I'm going to rewrite it. XY plus XZ plus YZ minus 500 equals 0. Okay, so there's our big G. So the big Lagrangian, the big mother of a function, big L, X, Y, Z, lambda, function of 4 variables. Oh my God. Yep. That's going to be your big F. So for us, that's X, Y, Z minus lambda. That's the Lagrange multiplier. Brand new variable, times your constraints. You're going to have xy plus xz plus yz minus 500. Woo! Okay. And you're going to basically extremize that function. You're going to do all your calculus on that guy. Get the partials, set them equal to 0, solve the system, get your critical points. Good news, you don't have to do the d-test. You already know in advance there's going to be a max or a min or both. Well, then how do you determine which one's the max or the min? Trial and error. Really? Yeah. You plug it into your original function, see who's big and see who's small. Now for this problem, we're only trying to do a max. So, okay. Let's go get the partials. So I need to get 4 of them. Well, why 4? Because this function is a function of 4 variables. So he's got 4 partials. So honor that. So now what? Oh, man. Let's see. When I take the partial with respect to x, well, the first term will be yz minus lambda is a variable and you're holding it constant, so that multiple, and then I'm going to take the derivative of everything inside the parentheses, but with respect to x. So I get y plus z. Fine. Set that equal to 0. get the partial with respect to y now. Okay, I get xz minus lambda times the quantity x plus z. Set it equal to 0. Fine. LZ, I get xy minus lambda times parentheses x plus y. Set it equal to 0. Fine. L lambda, when you take the derivative with respect to lambda, that's a variable, you're going to hold x's, y's, and z's constant. So the first term goes to 0, and then you'll just have minus everything inside parentheses, because that's considered the multiple of your lambda, and set it equal to 0. And I hope you see if you multiply both sides of this equation by -1, it's the same as your constraint, and that will always happen. Solve the system now. Now, folks, this is where it can get really dicey, and it can get hard. My plan of attack doesn't always work, but it's going to work a huge portion of the time. So I encourage you to try it first, and then if it fails you, then go try something else, okay? But the way I roll is, and I've found this has worked for me over the years, is I solve for lambda. In this case, I'm going to solve for lambda 3 times, and then start setting my lambdas equal to each other. Well, how come? Because I want to, usually I try to get everything in terms of x. So I try to get y and z, in this case, in terms of x's, and then I plug all that into my constraint, where then my constraint becomes a function or an equation of a single variable. And then I can get one of them, and then I can get the others. What did I just say? I don't even know what I just said. Let's just go do it. So when I solve for lambda for this first partial, I end up, when I'll add the lambda term to both sides, and then I divide both sides by y plus z. I'll call this lambda 1, even though there aren't individual lambdas. You know, they're all the same lambda. Then when I solve for lambda a second time using the next partial, I'll get lambda. I'm just going to call it lambda 2, but it's really the same lambda as the other one. They're all equal. And then here, I'll solve for lambda a third time. Oh my goodness. I'll call it lambda 3. And I get xy over x plus y. Now what? Now these lambdas have to be the same, folks. I mean, it has to be true that lambda 1 and lambda 2 and lambda 3 are all the same guy. You can't have different lambdas. Forget it. Well, then what? Well, how about if I set the number 1 lambda equal to the number 2 lambda? What the heck? Okay, let's just try it. See what happens. So I need the yz over y plus z to be equal to the xz over x plus z. It has to be true. Ooh, that looks like a mess. Well, how about if I multiply both sides of this equation by the LCD of both of those fractions? So that would be the product of x plus z, y plus z. Okay. So on the left, the y plus z's will cancel, and on the right, the x plus z's are canceling. But I still have like a hot mess. Like, oh, this looks terrible. Yeah, it's going to get okay. Don't worry. I'm going to distribute on both sides to eliminate parentheses and then see what I have. So on the left, I'll have xyz plus yz squared. And on the right, after I distribute, I also get xyz plus xz squared. Fine. But if I subtract xyz from both sides, the xyz term goes away. So that's like gone. Gone, baby, gone. So then what do we have left? Well, we got yz squared is the same as xz squared. But hey, we'll assume z is positive. That will allow us to divide both sides by a variable. Remember we talked about normally that's not okay? We're going to assume that we have a non-zero z value, which makes sense because we don't want our box to have a 0 height. And then we get y in terms of x. And is it always this easy? No. Sometimes you get y equals like 50x or something wacky. I'm going to save that for later. So now what? Well, I'd also like to get the other variable z in terms of x. So I'm going to set the number 1 lambda equal to the number 3 lambda and see what happens. Okay. So what I do is I have yz over y plus z had better be equal to that third lambda we got up here. That was this guy, xy over x plus y. That has to work. And then I'm going to multiply both sides of this equation by both denominators to kill off the fractions. Okay, that works for me. X plus y times y plus z. Fine. And then what? Well, over on the left, the y plus z's cancel, and we have yz times x plus y. And on the right-hand side, the x plus y's cancel. Fine. And we're left with xy times y plus z. This is messy, icky. Distribute xyz plus zy squared. That has to be the same as xyz, or excuse me, xy squared plus xyz. Okay, good news. Subtract xyz from both sides again. It's gone. So then we just have zy squared equals xy squared. Well, assuming y is non-zero, we'll divide it out and we get z is equal to x. Okay, great. Now, the good news is we have both y and z in terms of x. Usually they're not always going to be the same like this. This is an easy problem. So what you're going to do at this point is you're going to substitute into your constraint. Well, what do you mean? Well, remember our constraint is, look at what it was up here. It was up here. And if everywhere you see a letter Y, there's a couple spots. A Y is now the same as X. And so you'll substitute and you see Z in there a couple times, but Z also happens to be the same as X. And so you'll just substitute X for Z. And so you're going to end up getting X squared plus X squared plus X squared equals 500. Oh my, well, at least we can now figure out what X is. So that's one dimension of the box. We get 3x squared is equal to 500. X squared is 500 thirds. Wonderful. Now, normally when I square root both sides, what do I like to see?
Plus or minus.
Plus or minus, but we are going to throw out the negative in this case. Well, how come? Well, because let's face it, I don't want my dimension of my box, since this is a real life problem. If it were some other problem, though, you'd want both. You'd keep both. And the negative would probably give you a minimum or something like that. So you're going to get a plus or minus, but, and then since 500 is 100 times 5, I'm going to just reduce this to simplify the radical, and I'll choose the plus only. So this is going to end up being 10 times the square root of 5 thirds. Not a very nice number, but it's feet. And then since y is equal to x and z is equal to x, we basically have a cube. Yeah, we have a cube where all the dimensions are the same, 10 times square root of 5 thirds. And usually when you do Lagrange, you get a lot of wacky radicals for answers. This is very typical. So I just want to give you a heads up. When you get wacky, yucky radicals like this, you probably are on the right track. So don't freak out. Because last time when I put you in breakout rooms, some of you were kind of weirded out when you got a critical point that involved a fraction for a coordinate. It was like, that's okay. It doesn't always give nice, beautiful integers, okay? So then what? The max volume for this cube is going to be the dimension x cubed, because all the sides are the same. And so I'm going to end up getting, if I clean this up a little bit, 5,000 thirds times the square root of 5 thirds, very weird number, cubic feet will be the max volume for this box. The box is a cube. So they gave us 1,000 square feet of material. They asked us to maximize the volume for a rectangular box, and it turned out the box is a cube. All the dimensions are equal. That's how we're going to maximize this volume for this box. Lovely. And we're done. Yay.